record this separately so I can put it on YouTube as well. So this situation now, the test questions from this handout will be, and we'll annotate them. I dropped number 4, by the way, but we'll get to that. So number 6, number 8, number 11 is going to be extra credit. In fact, all the skipped ones will be extra credit if you want to do them. 14. And then 16 and 17. So just a few. And so it'll be a very manageable thing. All right, so this situation. This one is kind of complicated. There's, at least from an algebraic standpoint, as you'll soon see. So, but it's a good one in that regard. And I do want to point out one thing that you would have seen in your reading a while back in chapter 6 on the Atwood machine, which is just when you throw a rope over a pulley and use it to pull something. Now, when you do it this way, it takes just as much force pulling it down as is the weight of whatever you're trying to pull up. But if you use double pulleys, then you can, every new loop cuts the force by that fraction. So you do 5 loops on a multiple pulley system, and 100 pounds only takes 20 pounds of force, but you need 5 times the length of rope to do it. So it's like a chain hoist if anybody's ever done engines, and there's all this math stuff. And the thing is that for a classic Atwood machine, the acceleration of the falling mass, or both masses, will be the difference in masses over the sum of the masses. So it's sort of like a differential weight from it. And that's all this says here. So assuming mass 1's bigger than mass 2, then it'll fall in that direction. So this is a classic result that we'll be able to use in this problem. We wouldn't necessarily have to go through all of this, but you could if you wanted to. Actually, I forgot I'm not showing that screen. Let me show the screen that I wasn't sharing. So in chapter 6, as I was saying, Atwood machine, simple pulley, and part of our problem will look just like this. It's one pulley holding up another pulley with falling weights. And you could go through all this math, say here in the force approach, but this one equation right here, that the acceleration is some fraction. So forget about whether or not you think that's a complicated fraction, technically not, but something mass over mass will just be pure number. So it'd be some fraction of gravity. And so you would expect, so it's just trying to tune our minds to this problem, you would expect that the pulley system would get in the way of gravity, and in fact that one weight's heavier than the other, that this lighter one still is going to take away from the weight of the system as it moves. And so you have to kind of think through these things. So you would expect, if it was just one of the masses and you just dropped it, then gravity is the acceleration. But since it's coupled in this rope, and then going across a pulley, then you know that it's going to be gravity minus something. It's going to be something less than full 1g. It has to be. And so this tells us, go through all the force analysis, that the difference in masses over the sum of the masses is the fraction of gravity that this system will be accelerating. And so one of them, the magnitudes will be the same, except this acceleration's up and that acceleration's down. One can't go faster than the other, but they must go in different directions. So that's the idea, something that you were exposed to already earlier in the course. All right, so here we are back to the problem. So let's get into it. And so first thing we'd want to do is just sort of get a picture of this situation. So that's going to be a ceiling. You can make any surface that way. And I'm going to name one of these pulleys pulley A. And according to this problem, you have a 25-pound object that is on one side of the first pulley, and then on the other pulley, you have a 10 and a 15-pound object. And so hopefully you notice that 10 plus 15 is 25. So really, let me go back to my other color. So I'm not going to label the masses just yet. This will be pulley B. So this is the system, if you will, this kinetic sculpture that your artist friend wants to do. And I'll be trying to look at the chat line, but if you have questions, you can always stop. And so these context-rich problems have a lot of context to process. And so one end of this sculpture has one pulley hanging from the ceiling by a string attached to its center. Another string passes over this pulley. One end has the 25-pound object, while the other supports the other pulley at its center. Okay? And there's a 10, and so if I say that little m is the 10-pound and big M is the 15-pound, then I can just say M, and I can call this M plus M. So I'm generalizing this question instead of going directly with the numbers. I could save that for the end. Now there are alternate ways to do this problem, and I'm picking to generalize it in this sense. And it'll only apply to the situation. I need to improve the quality of that M right there. When the sum of the masses on the lower one equal the mass on the higher one, obviously. We could do M1, M2, M3, and that is not too bad. But I'll upload alternate versions of this later. So we've drawn a decent diagram of this system. I guess it needs to be attached to the thing up here. There we go. And so we have drawn our situation according to the givens in this statement. And then they want to know, so the question is wants to know if ignoring the mass on the pulley of the string will remain stationary, okay, when those are falling. Okay, so here's the thing. Down here, that bigger mass has to fall down and the lighter mass has to go up. And I don't think anybody needed to come to college to figure that out. Okay, the heavier one's going to fall, and it's going to pull the lighter one up over that pulley. So we know that the lower one's going to move. And the question is, will that motion cause the whole pulley system, pulley B, to fall as well, or will it rise while the M plus M falls? So there's not many choices. Either this mass here will rise or fall, which means the pulley B system does the opposite, or it doesn't move, okay? And we don't even need to know what its acceleration is other than, is it 0 or not? If it's 0, it doesn't move. If it's not 0, it does move. He didn't care, the artist here didn't care what it was. So if she, he, whoever wants it to move, then they'll have to figure out a way to make it move. Add some weight, do something. All right, so now we've drawn a nice, pretty picture. So now let's think about the factors that are important. So if you have ropes and there are masses on those ropes, then you have tension in those ropes. And so it would pay to say, well, we've got tension in the rope here. We could call that tension 1. We've got down here, similar kind of thing. These ropes are going to have tension. We could call that tension 2. We know since big M is larger than little m, that those accelerations are going to go that way. We absolutely know that. And so now we sort of blended our diagram with the force diagram a little bit, just to focus our mind on the way these interactions are working out. And now we can write some equations, or what we'll do is we'll draw some force diagrams. So I'm gonna take the comfort of a chair here for a while. So up here on the top, I know that I'm going to have a weight going down and a tension 1 going up. That's one of the things there on that side. And then this other one, I know that I'm going to have double the tension 2 equal to that tension 1. So let's use these cool features here. So this right here, that's what is going on in this situation. Now, the problem specified that the pulleys are massless, okay, and frictionless, and so are the strings, or we're making that assumption. Of course, in reality, that's not true. But we do that for simplification here. And so, but to know that this tension 1 would have to be equal to the forces below it. And so the tensions in those two ropes are related to the masses, and so just there's 2 of them. And so the tension 1's got to be equal to double tension 2. And so every textbook in the universe would say that. I didn't do this exact problem in the textbook, but I will be adding it to the textbook later. So now I have some force diagrams for that top part of the puzzle, which means that I can write equations. So I have T minus M plus mg, or the weight, so minus that weight, so T1 rather. And that's going to equal, and here's what's not obvious, it's going to be minus that same weight, but the acceleration of the pulley B. So pulley B, meaning this thing here, it is going to be going up or down. I don't know whether it's going up or down, but it's going to have a value, and it's either going to be 0 or not, okay? We can make that leap. Of course, here's the thing we absolutely know, is over here is that the acceleration of this m plus m thing has to be the opposite of the acceleration of B. So, to kind of link the things with color there, that has to be true. one has to be the opposite of the other. Whichever way, if the M plus M thing is going up at 1, then pulley B system must be going downward at 1. And so pulley B could be moving at a speed different than either of the masses on it. Okay? And so we don't really care what those values are right now. We just want to know, is it moving or not? That's the simple question, which doesn't have a simple answer in this case. And then we also have T1 equals 2 times T2. So we have those things there, and so we could sort of simplify this set of equations for this top part. Instead of having T1 in this top one, we could double T2, and we would know that this would equal M plus M times G minus M plus M times AB. And if you look at that, they have a common factor, the quantity M plus M, and then if you could pull that out, you would have some amount of mass, the sum of that whole mass there would be G minus whatever the acceleration of B is. So that makes sense. We know it's going to be less than G. By how much? By how much that lower system is accelerating. All right, and so the tension would have to equal that. So we've written those. So now we can't do much with that because we don't have any numbers to plug into that. So we have to keep on going with our math. And so down here, if I do some force diagramming, so this smaller mass would have a weight down of mg. That would be in balance with T2, and its acceleration is upward. And we could call that A2, since it's associated with T2. We could have called the top one A1 instead of M plus M, but I wrote it that way. And then this will be a big mg. One drawback to little m and big M is it would be easy to mess up the math simply by writing the wrong letter, capital or not. And so that one is going down. A2 is going down that way. So now I can write, I've gone from a diagram to force diagrams, or a picture to force diagrams, and now the force diagrams let me write equations. So T2 minus mg will equal ma2. So A2 is associated with both of these, and since it's going up, I made the ma positive because A is positive in that case. So that's taking us all the way back to all that whole sum of forces thing, Newton's second law, sum of forces equals ma all the time. So you've seen that in videos, the book. Go get a tattoo, so you never forget. All right, and so this means that we would have just mg plus ma2. So if you think about that, common factor of mass, but it's g plus acceleration. All right, so we have that, and because of this classic Atwood situation, all right, we know and we could get it from doing a bunch of force equation stuff, or we could just say, I know that this acceleration is going to be the difference of masses over the sum of masses times g. That's straight out of the book. Straight out of, if you Googled classic Atwood machine, somewhere on that page it's going to tell you exactly this. It might have M1 and M2 instead of big M and little m, but it's going to be the same thing. And so we can immediately use that. This right here is going to go right into there. All right. So this means T2 would equal mg plus, now I'm going to have that whole m plus and minus stuff fraction g. So A2 becomes, it's still got an mg, but then it's got this m minus m plus m business going for it. Which is nice, because now T2 could be, I could immediately compute the tension in string 2. It wouldn't help me answer the question, because the question wants to know, is that larger mass at the top, is it moving or not? Tension 2 doesn't tell me whether or not, tension 2 just tells me how much force is in that rope. So I'm not going to bother plugging and chugging numbers, and that's one of the things that can mess you up is you think that putting numbers in will help you, and actually it tends to not, because if you don't carry a lot of decimal places, then you will propagate rounding error in your calculations. So, all right, so now we have, what we need to do is we're going to bring this equation, oops, I want a different color. This equation and this equation, we need to bring those together. Okay, so I'm going to write out a bunch of stuff that brings us, I'm basically going to substitute T2, the blue version down below, into the red version up above, and I'm just going to do that on the fly here. And so this means I get a 2mg plus 2mg. Now you don't have to ever do this much on a test, but it's more about thinking through the problem, and then there's the math challenge that goes with it. So there's all of that, and for this course, it doesn't really matter much that you could simplify that and solve it for AB, but I'm just going to go straight to it for a number of reasons. Sake of time, you're not ever going to be required to do that in this course or any course that I suspect, and it doesn't do anything but take up time. If you were in the afternoon class, I would be less forgiving and concerned with your plight. So what this means is I have this thing after I do 4 or 5 lines of algebra to solve for AB. And so now I can know if AB is moving, and AB will be the minus of the other acceleration. So if AB is moving, then that weight is moving. That's all I need to know, all right? And if you were to plug and chug some numbers in this one, you'd have 1 minus, since all the masses, these are weights, so I'd have to divide every mass by 32.2, but since I'd be doing it everywhere, it's pointless to do that. So I could just go 4 times 10 times 15 over 25 squared, because that's what 10 plus 15 would be. And this means I'm going to have 1/25 g. So that's not 0. So it's moving. So not 0. So it's moving. And we've answered the question, and we really didn't even have to compute what the acceleration is in any particular number. All right? And that's what the math lets us do. All that math that I skipped a few steps with in here. So there's a little bit of magic happening there, and there's that problem. So I've worked the problem a couple of ways, and I'll when I scan these notes, I'll add in a few versions of this problem. But again, you don't have to. This isn't a test problem. This is a demonstration problem. So let's move on to number 2. Something a little less challenging. All right. So this is an elevator problem, and you have an elevator problem on the current forces, prep Coke, the mini version. And so this one is a similar kind of problem. And so you under maximum acceleration for these elevators during normal operation, you decide to measure it using your bathroom scale. And you're apparently not bothered that people are wondering why you brought a bathroom scale onto the elevator. And elevator, it rests on ground floor. You get in, you put your scale on, you stand on the scale, reads 130. So I want to do some interpretation. While the elevator, you get in, the scale reads 130 pounds. What that means is that the normal force is 130 pounds. So that's just standing on a scale. Your weight is pushing down towards center of Earth, and the scale reading is the reaction force. And so when there's no acceleration, then that normal force, the scale reading, is exactly what your weight is under Earth's gravity, where it's just G plus 0. All right? So when you read these things, how do I connect facts that are given in some problem statement or some situation that we're trying to model and put that in physics lingo? Well, the normal force is the surface reaction force. We've read about that. You've taken notes about that. And now we're going to solve problems. And we need to get it in our heads that the surface reaction force, the normal force, meaning perpendicular to the surface, will be some fraction of the weight force. If everything's flat, it's 100%. It's 1/1 is the fraction. But if things are tilted, then it'll be some fraction of that, as we've seen in other problems. So that just reading it, we have that. But then you continue standing on the scale when the elevator goes up. So when the elevator goes up, that means we're dealing with some sort of addition, either in the positive or negative direction to gravity. If you're going up, then the floor is pushing into your scale, so that's kind of squeezing that scale more, so you would expect it to go up, which is what it did. It went up to 180 pounds during that part. So an elevator will accelerate for some amount of time and distance, and then it'll reach a constant speed. When it's constant speed, acceleration 0, and the scale would go back to the normal reading as if you were standing on level, flat, non-moving ground. And then as the elevator comes to a stop, it will decelerate. So now we're subtracting from gravity, and your weight would go down because the floor is starting to move away from your feet, if you will. You can feel that. You feel this on elevators. When it starts going up, you feel it push into you. When it starts to stop, you feel it kind of pull away from you, and opposite. All right, so we have we've kind of decoded the question, and you should take time to do this. Hopefully it doesn't take as long as it does for me to say it, but you should do that. You should take some notes, write something down. So here's the situation. Here's the point particle of you, the person, okay? And there's your weight force is always directed straight down towards the source of gravity. The surface that you're standing on, it really wouldn't matter whether it was a scale or just the ground or a stair step or anything. It is the normal force, all right? And so we have that. And since acceleration was up, Now we have a force diagram. This is the force diagram for the part of the problem that we're concerned with, which is during the motion, because that's when, during the trip to the 50th floor, the greatest scale reading was 180 pounds, and that would have to be when something was adding to gravity, because you couldn't get the scale reading to have more weight, apparent weight, than you actually have. So these problems, when you're dealing with the normal force, which is always going to be like when we're dealing with friction, which you've seen plenty of so far, you have an apparent weight and a true weight. True weight is what your weight would be flat ground, no acceleration. Apparent weight would be adding to or taking away from weight by virtue of how forces are applied or how unbalanced the forces are. All right, so now we have a really simple equation here. The normal force is positive up, weight force is down, and that has to equal ma, which is also positive. Had that a been going down, if we were coming from the top floor down, then it'd be minus ma. So this means, so we want to know, you wonder about maximum acceleration. Okay. Okay, so that's what we're here to do, is find that maximum acceleration. So that means A, excuse me, MA will be, I'll just be more explicit here, you divide both sides by M. So A is going to be N minus mg over M. And so how do we do that? Well, the normal force, the max reading associated with the acceleration we're concerned with was 180. Your true weight, mg, is 130, and the mass, well, it's 130 pounds, and so we would have to divide 130 pounds by the gravitational acceleration. So this little thing here is just weight force over g, if you will. All right. So, in fact, I'm gonna weight force over g. Be a little bit more general. And this means that in this case, acceleration is approximately basically going to be 50 over 130. In fact, what we could do, in fact, I'm going to change this up a little bit to be a bit more what you'll have is 50 over 130 over g, which just means that you have 50 over 130 times g, so some fraction of g. So I want to rewrite it that way because we're always adding to or taking away from the acceleration due to gravity, which will change the weight, go from true weight to apparent weight in all of these situations. And so, or you could just say 5/13 g, and in this would be 12.4 feet per second, or it would be 3.8 meters per second. And so that would just be if you use g of 32.2 for if it's a system of feet, or g is 9.8 when it's system of meters. So if you needed a number answer, that would be, so g is 32.2 versus g is 9.8. So you have to pay attention to the system. A lot of people missed problems simply because they were in the wrong unit system. They had done all the math right, and had it asked for it in feet instead of meters or vice versa, you would have had the right answer. I gave those away to people on the last celebration that most people still need to use up their attempts. So a few people have contacted me and I've helped them through, but not enough people have contacted me about that. So I've purposely lightened the load so that people can get to it, but you will almost certainly have to contact me in between your attempts. So don't worry if you have a terrible first attempt. You have 3 total attempts. Goal is to make the test a learning experience. And I want to remind you, I put it in an email and an announcement. If we were face to face, these exams would be group exams. You would have 3 hours and you guys would be walking all over the place, talking, sharing notes. I'd be answering questions, giving ideas, trying to keep people in bounds. And those tend to go very well, and people learn something in that process. And so I like exams that way, especially in a course like this one. But we're online, so it's hard to have a group exam when you're online. You could do it, it's just really clunky. So multiple attempts where you talk with me in between your attempts is one way to approximate that. And you're free to work in groups. There's nothing keeping you from working in groups on these things. So do that if you want to. If you don't, then just work it out with me. But you have to ask questions in between attempts. Otherwise, you probably won't be that successful. All right. And we'll continue to do that next semester too. More elevator stuff. Elevators are great physics things. Elevator has all the latest safety features and will stop with 1/3 G in any emergency, and they want to put a decorative lamp hanging from the unusually high ceiling, okay? So, acceleration, G/3. Each section of the lamp weighs 7 newtons, so it's going to be 3 things hanging on a thin wire that the power is going through. And we want to determine the thinnest wire that can be used for each state of the lamp, calculate the force on each wire in an emergency stop. So if we draw a picture, so top of this unusually high elevator, I don't know that, that would be unsettling to look up and God, there's a thing hanging over my head. If it stops abruptly. All right, so here we would have this block diagram of these nodes or lamps. So 3, 2, 1. There are 1, 2, 3 in ascending order there, and so this would be tension 1, which would be equal to the weight of that lower one. This would be tension 2, which would necessarily be equal to the weight of the 2 below it, and tension 3, etc. So relatively simple setup, if you will. And so let's just start. Let's start with the bottom light. So there's going to be a tension 1, and it's going to have whatever the mass of this is. So this is, this is a mass 1. We'll call this mass 2. I'm going to take them out of there so we don't. Mass 3. Mass 2. Mass 1. All right. So that has to equal whatever mass 1 acceleration is. These are all going to have a common acceleration. Now, what do we know? That acceleration has to be 1/3 of G. Okay, so this piece of information here from the top, okay, this is how that comes together so that we have something that we can work with. All right, so let's try to simplify this some more. So this means that T1 will equal, and so M1G, if I add this to both sides of the equation, this middle part sort of goes away, M1G plus 1/3 M1G. Well, that's nice. So out here, this is really coefficient 1 would just be 3/3. All right. But we don't even have to mess with that because we already know that each lamp weighs 7 newtons. That's the weight of that lamp. Those are 7s. Yay. So that means T1 is going to be 7. I'm going to just leave it. We know it's newtons. Plus 7/3. All right. And so that's going to be 28/3 newtons. How do I know that? Well, multiply by that fancy formula 1, 21/3 plus 7/3 is 28/3. All right. So, yay, we have that part here. So now I can go to the next one. T2 is pointing up there, and it has 2 7-Newton forces weights underneath it. These weigh 7 newtons. So we could just say -7 minus 7. Okay? And so that's a sum of forces. That up tension in between the second and third light bulbs has a 7-Newton bulb underneath it on a string with another 7-Newton bulb. So the up tension has to equal the sum of the down tensions, or minus both of the opposite ones. And then its acceleration piece of the puzzle, so whatever their masses are, which we end up really not caring, again, under the emergency acceleration limit of g/3. All right? And so, again, T2 is just going to equal my brain here. So if M1 plus M2G will be an M1G plus an M2G, which would be a 7 plus 7/3. So this is going to be 14/3. Whoops, I should need to write that up here. That's going to be 14/3 newtons here when you look at that part. Okay, so now I'm going to bring these two 7s over, add 7, so that's going to be 14 newtons over here. And so what do you have? You have 14/3 plus 14, and if you do the math on that, you get 56/3 newtons. So what's going on here? Looks like we went from 28/3 newtons on the bottom plus another 28/3 newtons on the next one. So guess what's going to happen for the last one? It's going to be another 28/3 added to that. And so, or you could just say T3 minus 3 times 7, 21, okay, will equal, and again, you would have, instead of, we started off with a 7/3 plus another 7/3 plus another 7/3, otherwise known as 21/3. And so that means T3 is going to end up being 21/3 plus 21. And that means you have 7 plus 21, so 28 newtons. So some of this math, not really necessary. You could have just kept adding 28/3, and you would have had 3 times 28/3, which would be 28. That would have been, it would have been perfectly okay to just, go from that to go, well, this happens, it's a 3 times that, because it's 1, 2, 3. Perfectly good. All you have to do is write that. There's 3 of these in a row. It must be 28 newtons. Problem solved. These are technically simple problems, but anytime math comes into the picture, there will be disputing about how simple those are. And your thinking is what's most important. 4, I'm skipping this one. And you can too. And number 5. All right. A job devising stunts. So here's this long story, okay? And so basically in this story, you need to save the good guy who, or maybe it's Black Widow, who knows? But draw a stick person here. Okay. So somebody is on the front of this train, I think it's a train, and we need to make sure that they don't slip off and get crushed by the train. And so the hero is out there on the front, the bad person wants to cause that person to fall, but you have control of the system, and you open the throttle to accelerate it so that the force of friction, okay, that's on the person will somehow so the force of friction would be pushing up, weight force would be pushing down, and then if you can press the train into the person's back, you can basically squeeze those surfaces together and make the friction a bigger deal than it would be if it wasn't moving. Because if it wasn't moving, you'd have to have Velcro or something, and to keep you from falling off the front of the train. But if the train's moving into you, kind of helping the friction, if you will, by squeezing those two surfaces together, then that's what we're doing. So the force diagram for this, so this will be the person, our hero, who has a weight. Gravity wants to pull the person to the ground. Friction is now, normally we would have the normal force, but the normal force is always perpendicular to the surface. That's the trick. So up until now, we've always had things on an inclined plane or on the ground, and normal was always perpendicular to the surface, and it would have been going up. But this time, friction is what's going up. The normal force is headed that way. The acceleration is also in that direction because we're trying to push the train into the hero so that the hero doesn't fall off the front of the train. So we have a nice, relatively simple problem here. So if I sum the y forces, which sum of forces always equals ma, and in this case, we're trying to make sure that there is no acceleration in the vertical direction, so that's going to be equal to 0. And so what that means is that the friction force, in fact it's the static friction, note that they give coefficient of kinetic friction and coefficient of static friction. We have to pick one. In this case, we're going to pick static because we want the person to static friction's more. If we let more of that happen, then they would slip off the front. So the force of friction has to equal mg because those are the only two vertical forces. And this means that the coefficient of static friction times the normal force equals mg. So we have that. Then we sum the x forces, which have to equal ma, and we could say x in this case if we wanted to. That doesn't equal 0, okay? We know that we're having a non-zero acceleration so that we save. So this means that n equals ma. And so what we can do is this goes into there, and we have static friction times ma equals mg, which means acceleration, because the masses drop out, will be g over the coefficient of static friction, which we are dealing with pounds. So that's going to be well, actually, we don't even have to. Nice thing here is you could say 1 over mu sg, which means A is going to be roughly 1.7 Gs. And I think that makes more sense. Now, if you had an accelerometer that was telling you how many feet per second, but you could just multiply that. And so that's going to be in feet per second, or that could be 16.3 in meters per second if you wanted a number. Okay, but almost 2 Gs, so almost double your weight. That's how much force would be pushing into the person. That would be a way to characterize this. You have to make sense of these things, and you can handle your own weight pushing into you. You may not want to do that for a long time, but it wouldn't kill anybody to do that. I think 4 or 5 Gs is where people start to buckle under it, and I forget how many Gs will guarantee kill you, but I have to look that up. All right, number 6. Number 6, this one will be on the Coke. You do have a problem similar to this in one of your lectures. So, all right. You're planning a log cabin in Minnesota. You will pull logs up a long, smooth hill. Okay. This is an inclined plane problem, so I will draw an inclined plane. So you will pull hills up a long, smooth hill. So I draw a inclined plane. And what I'll do, inclined planes have an angle. if something's moving up that inclined plane, I'm dragging it by a rope. Okay. So that means there's going to be tension. Okay. And that means that some portion of the weight, well, we know the true weight is straight down. Okay. So that means some portion of the weight is directed that way, and another portion of the weight, some fraction, is directed that way. Now, I highly recommend that you just use what's been given in your book. So the fraction of the, and remember, when we do inclined planes, we tilt our axes, and so I'm making up the hill positive, and that when we rotate our frame of reference, the sine and cosines shift from cosine x sine y to cosine y sine x. And that was lots of writing and reading and talking about that in prior lectures and textbook readings. Do I need you to redo this every time? No, just know that when you tilt something on an inclined plane, okay, that the weight, there's apparent weights in two directions. There's an apparent weight perpendicular to the surface, that'll be important for friction, and there's an apparent weight parallel to the surface, which will be important for motion. It's part of the summing of forces. Okay, so use that as opposed to deriving it every time. That's not useful in there. And so this system here this mg and that angle, all right, and so we could all right, so this one that's parallel or adjacent to the angle theta is going to be the cosine, and the one that's opposite that angle has to be the sine. Okay, so there's the way it plays out on the left in the actual thing, and then there's just the pure math part of it in that coordinate system. All right, so come back to the data. Oh, I have to apologize. I forget frequently. That's 30 degrees. That's meters per second squared. So, and there's some numbers where it's like supposed to be 10 to the 20th or something, and it's 1020. And so I'll try to fix that later. When I copied them over from one source to the Word, then it dropped all that formatting, and I didn't notice it until now. All right, so sum of x forces. And remember, we are trying, and it says, I wrote, I need that to be y, not x. All right, so these are going to be 0. So on a surface, whether it's tilted or not, we tend to not have the object that's moving parallel to that surface move, bounce, or whatever. And so in the y direction, which has been tilted, no acceleration. So still would equals ma in the y direction, but no acceleration in the y direction means it's 0. And so what this means is, oh, by the way, I forgot to, up here, that normal force, again, perpendicular to the surface. So N is positive, though it's tilted, mg cosine theta, for the vertical parts. There's nothing else vertical happening there, all right? And so that equals 0. So N equals mg cosine theta. Now, I would encourage you, every incline plane problem where there's no other force in the game than an up force, surface reaction, and the weight component there, you could just write the normal force as mg cosine theta. Now, if we had a rope and we were pulling up at an angle relative to the inclined plane, then it would have an extra term in there. It doesn't. So you could just know that the normal force is going to be that every time. All right, so now let's sum the x forces, okay, which have to be ma in the x direction. It's not 0 in this case. So, because you are trying to figure out how strong a rope to buy by maintaining a non-zero acceleration. All right, so this is going to be, so I'm going to have it, oh, we forgot to add in here that there's friction that's opposing that motion, okay? So, and we didn't put tension in that force diagram either. So I'm going to add that in as we go. So T, we're defining up the hill to be T. So T minus that fraction of the weight. And I want to write that as I say it. You see mg, think weight. You see sine, cosine, or tangent, think fraction of. Those are the most basic. Of course, sine, cosine, tangent, they literally are fractions. Opposite over hypotenuse, adjacent over hypotenuse. It's a fraction. And so any trig function multiplied to, say, a physical quantity like weight or a force would be a fraction of that weight force. So tension minus some fraction of the weight force, okay, heading down that direction, minus the friction force, okay, which we know that friction is mu n. Hopefully we know that by now. And it's going to be kinetic. Those are the, those have to equal ma. Now, just to be clear here, because it's easy to get lost, this and this are those opposite the tension forces. Here's that friction force, and here's that fraction of the weight force. All right? And the tension force up here, all that, and all of those sum of forces, the tension going in one direction, the fraction of weight and friction opposing that tension, or creating that tension really, all of that summed together, accounting for directions, has to equal ma, Newton's second law. That's what we're doing when we write these sum of forces. And I labor this point because it takes a fair amount of time to sink in the human brain. You know, as a math major and a physics minor when I was in your shoes, and it wasn't like the first time they showed it. I'm like, oh, of course, duh. Why didn't I think of this? You know, it took a while for it to really sink in. All right, so this means I can solve T is going to equal ma, and I'm going to bring the other two things over, okay? So plus mg sine theta and plus mu kn, but mu k is some number, and n was mg cosine theta. And so that means that T would, I could just write it as m times these other things. Makes things a little bit easier. And because it was a 30-degree hill, well, we'll put 200 kilograms. The acceleration that we wanted, I don't know how someone's going to know that it's 0.8 meters per second squared, but that's what they did. Sine of 30 is half, all right? So you took a trig or a pre-calc course, and at some point you would have known that. So that's going to be half of 9.8. The mu k that we're looking for is 0.9 according to the problem, and you have a 9.8. Cosine of 30 is root 3 over 2. You were forced to memorize this, or you should have been at one point. So that's 1.73 over 2. You could punch it into the calculator too. It's all relative. And so what you get is a few thousand newtons. I'm pulling these logs up. And that's about 600 pounds. And that's probably what we would be looking for if we went to the store for rope, is what is this rope rated for? And it would say 1,000 pounds or 500 pounds or whatever it is. And so you need a rope that has a max limit of at least 600 pounds, probably more, just to give it some play there. So that's, a pretty basic inclined plane problem, all right? And so there's some math there. Then this next problem is also going to be on the Coke. I'm going to do something here. So this is going to be a Coke problem, but I will give you a little bit of hint in that this one is a pulley and an inclined plane problem. So you're going to have some angle, some mass, a rope, and in this situation, double the mass. So this is like an Atwood machine and a inclined plane problem mixed together. And you're going to need to think about your XY system, and you're going to know that there's a normal force here. Gravity would be straight down. That's the angle again. And there's going to be some other forces. You're going to have to think about what are the other forces on this diagram, okay? And you'll do the same stuff that we just did on the last problem, and to some degree the Atwood machine kind of problem, and you'll get an answer. And so this will, it's no more difficult than those ones. I would say that it's no more difficult than the one we just did. You're just going to be having to deal with two force diagrams. I drew the one for the mass here, but then there's going to be this falling mass. Okay? And so, you have to think about, the tension in the rope. So our Atwood machine, they were straight up and down, and those tensions were directed up towards the pulley. Now they're still directed towards that pulley, but you are dealing with two coordinate systems. There's a coordinate system for this part of the puzzle, and there's a coordinate system for that part of the puzzle. So this one is your standard XY, and this one is your non-standard XY plane. This is every physics textbook in the universe has this problem, and what's different is the values of the masses and the angle and the friction. That's all that's different in that. There is one last thing I want to alert you to so that you're not completely blindsided by this. Right here, you find that you can push a 50 kilogram package at constant speed along a level floor along the same materialist ramp. You need use this as a separate mini problem that you're going to find the coefficient of friction. All right. So you might want to start with that. It's super simple because it's flat and there's only if you move it at constant speed, that means acceleration is 0. So that means sum of forces in the x direction have to equal 0 because friction is balanced with the applied force. And so it's a simple, straight up, easy computation. And either start by finding mu, but you will definitely have to find that before the problem is over to get the answer. Okay, so one of the reasons why this is going to be a shorter coke is I've given you this practice one from lecture, and then this problem is really 2 problems. All right, so it's a small one and then a slightly bigger one. All right, so that's going to be on the coke. I've set you up. I've nudged you into the arena. But I didn't push you off the cliff. All right. All right. This problem here. After graduating, you get a job in California, rent a truck for all your possessions. Instructions with the truck tell you that the truck, when fully loaded, is 20,000 pounds, and that the towing hitch has a maximum strength of 1,000 pounds. Before you leave, fully weighted truck is 15,000 pounds. So trick is how much of that is useful information. Same time, you weigh your car and find it weighs 3,000 pounds. You begin to worry if the hitch is strong enough. So if the hitch is strong enough, okay, so the towing hitch has a maximum strength of 1,000 pounds. That's definitely going to be an important piece of information. I don't know if the weight of the truck is going to be a problem or not. Fully loaded truck was 15 and your car was 3,000. So I think we're going to be under the 20,000 limit for the truck, so that the weight of the truck may not matter at all. All right. You know that air resistance will increase as the car goes faster, which is true because the drag force, one of its factors is speed. You estimate that the sum of forces due to air resistance and friction on the car is not more than 300 pounds. Okay. So without risking breaking the hitch, what's the max acceleration you can have on level ground? All right. Let's take a look here. So for part A, what are we going to have? We're going to have some weight that's down, some surface reaction force that's up, the normal force. The mass acceleration of the system, It's always going to be a thing. And then there's this 300-pound resistance to that. So we have a force diagram. Now, according to the problem, the weight of the car, 3,000 pounds, because that's what you were towing. And this is what's maybe not the most obvious part of the problem. Takes some thinking, asking questions. But the sum of forces due to air resistance and friction on the car is not more than 300 pounds. So that must mean if we're talking about resistance to the car, then we must be talking about the weight of the car. And so that's that. Now we have this limit, okay? Towing hitch that we're towing the car with has a max limit of 1,000 pounds. So, some ways that you can look at this. This hitch, limit of 1,000 pounds, and then there's going to be some force on it that's going to be our MA, the sum of those forces. So the difference between 1,000 and MA can't exceed the limit of the hitch. So we can pick this problem as a demo problem because it requires a non-formulistic way of thinking that I can write with a formula. And I just gave one description of that. And so I'm going to write out this formula. And so this mathematical statement matches the sum of the information in the problem. The towing hitch that you rented, okay, is 1,000 pound limit. Whatever acceleration you put on the car, all right, is going to inch its way into that limit, okay? And so the difference between those two things has to equal the resistance to those things. It's one way to write this out. You could say the difference between the limit on the hitch and the resistance will equal the MA. I don't know which one's better because everyone has a different way of thinking about that. So, but MA is going to end up being less than or equal to 700 pounds. You can just go straight to that. I can't have the sum of forces be bigger than the limit minus its resistance. You could just go straight to that. There's lots of ways to write it, which means if I have to divide both sides by M, okay? And so that means A is going to be less than or equal to 700 pounds, and it's going to be the mass of the car is 300, well, the weight of the car is 3,000 pounds, but I have to divide it by that 32.2 feet per second to deal with the mass. Okay, and that's it. These problems, you could treat mass and weight the same and do all the math right, except your input values would be missing the G factor. And so you have to be mindful of that. And I will predict that people will forget about that and get frustrated because they're not getting the right answer when they're off by the factor of G. Okay? So be mindful of that. And if I see that in your notes, then I can give you most of the points back. So the acceleration can't ever be bigger than that. And so that's, maybe 1/4 of G, roughly. You're not likely to have a car give you more than 1 G. All right, so that was on flat ground. What about driving up a 5% grade? All right, so again, here's our classic incline plane problem. All right, so we would have our little tilted system that everybody pulley loves. And let's see here. So we're going to have a normal force there, an mg sine theta force there. I'm going to change that color. Let's see here. Mg cosine theta along the y. And then there's also going to be that 300-pound resistance force, if you will. All right, and I guess an MA up the field there. So again, we're going to have a little bit different. We can reuse this limit that we had before, the difference between the hitch limit and the motion, the force, if you will, associated with motion. It's got to be less than still that hitch limit, but now I've added, since I'm going up an incline, well, now there's extra. I've just added to the resistance. So instead of just the air resistance, now there's an extra little chunk of that weight that's trying to pull you down, and that chunk of weight that's trying to pull you down is that mg sine, that fraction of the weight parallel to the surface. I talk about that extensively in my textbook. All right, so MA is going to be less than 700 minus that additional weight parallel to the surface. So notice that's essentially the same as part A, just tilted. So if you had it in your mind that there's this mg sine theta portion of the weight that always is opposing motion on an inclined plane, or causing it if it's pulling it down, you could just go straight to this. All right, so A has got to be less than 700 minus 3,000, because that's what the weight is. So mg is weight. You wouldn't have to you wouldn't want to put 3,000 times 32.2 or anything. Know that mg is that 3,000. It's important that you know that, and that becomes second nature to you. It was a 5-degree hill, and again, we're going to have the 3,000 over 32.2. So that means A is going to be 4.71 feet per second. And that's less than the 7. We would expect it to be less, because now we just sort of, you probably felt this if you've been in cars and whatnot. And part C here, I ran out of room almost. So the steepest hill, what is the steepest hill that you can drive up at any speed? So this is not obvious. This is implying that acceleration up that hill is 0. Okay, that would be your steepest, because if, acceleration is what, if I increase the incline, I have to decrease the acceleration so that I don't break the hitch. So the steepest hill would be making acceleration as low as I can and still move forward. And so acceleration have to be 0. There's nothing in the problem that just tells you that straight up. There's no formula to solve that would tell you that. It's thinking. It's scientific reasoning about the physics of this. And so if I reuse this thing that I just used, okay? So this right here and this right there, they are the same thing. It's just still the same situation, but acceleration goes to 0. All right, And that changes things up a little bit. And so now mg sine theta has to be less than or equal to 700. And so that means theta will be the inverse sine, that's why you took a trig course, of 700 over mg, which is the inverse sine of 700 over 3,000, or 7/30. And if you plug and chug that into a calculator, you will get 13.49 degrees. Sine's always y over x, but it doesn't really, I'm sorry, thinking a tangent, never mind. So simple calculation there to get that angle. 1030. This Star Trek problem will be extra credit. So there are people who may need or want extra credit. So I'm going to make some of these problems extra credit, and those two are going to be extra credit. And the system, I don't believe that the new Blackboard lets me assign extra credit questions, so these will have to happen offline. So I'll try to remember to make a separate handout for that so that it's clear. And if I don't do that soon, perhaps one of you can say, hey, where is that extra credit thing you mentioned? But you know this, so hopefully you're taking some notes. All right. New device for testing how to measure some small objects. 2 light strings, attach one at a support. So let's take a swing at drawing our picture. And so there are 2 objects. One of them is at a angle different than the other. This theta 2 is larger angle. And the known weight of the thing with the smaller angle. So this one, we know that the weight is 2 newtons, all right? There's going to be some tension in this thing, and I'm going to say T1, so this is mass 1, but the angle, theta 1's right there too, so this is a T1 cosine theta. And that's important that we know that. And then over here, this is just going to be m2g, but we don't know. We want to find out what that weighs, or what its mass is. And same thing over here, this is going to be a T2 cosine theta 2. I got to put theta 1 there. Now we've only accounted for what's the up portions of this thing here. So these theta 1 and theta, these alternate interior angles, you had to learn that in a different course. That's why you were forced to take that course. And in this problem, though, power supply is turned on to give it electric charge, move away from each other in electric force. So there's this electric force that's causing them to push out like this, because otherwise you wouldn't expect these things to hang this way if those are strings. You know, if they were spears that you can't see poking through the roof, then it would make sense why they hang that way. But there's no reason for them to hang that way unless there's a force pushing them out. And in this case, these forces, electric forces, are equal and opposite. In fact, they have the same structure as Newton's gravity, just different numbers. Well, that means there's also components of tension in each one. And if the up ones are cosine, then the across ones are sine of the corresponding angles, so theta 1 or theta 2. And so I've essentially drawn the two force diagrams there. Okay, so I don't want to waste a lot of space. Theta 1, we're told, is 10 degrees, and theta 2, we're told, is 20 degrees. And so we basically have our force diagrams laid on top of the picture itself, and so this will be good enough for our purposes. Here's the thing is, if you look at either one of these sides, so let's just, look at that right there. It must be the case that force, this electric force that we just, it's some force in the system, equals that horizontal part of the tension. Well, it's the same force that's over here on the other side. And so it must be the case, given that we have force is going to equal T1 sine theta 1. They're equal and opposite because it's holding them in place. And it also equals T2 sine theta 2. These are all, those two tension components have to be equal in this case, in the horizontal direction, because these forces are holding these objects with some sort of weight in place. All right, so we have that going on for us here. Now, we also can take this part of the puzzle. So T1 cosine theta, that's going cosine theta 1, that's positive going up, would have to equal this M1G going down. And so that means T1, since I know what mg is, it's 2 newtons, over cosine of 10 degrees, we have that. And then over here, T2 cosine theta, let me go back and do that. And then let's see here, we'll do this one in red. T2 cosine theta 2, gotta not mess that up, would be M2G. This is the mass we don't know. We don't know what this one weighs. So T2 would we just have to put a pin in this one here and come back to it. Well, I can take advantage of the fact that basically what I want to do, let me get a good color here. I want to take this fact about T1 and bring it into there. Because what that does is it basically makes the only thing not known in that balance mass 2. So if I so instead of T1 sine theta 1, I'll write 2 over cosine 10 sine 10, okay? And that has to equal, instead of T2, I'll write what it is down here, M2 G over cosine theta 2 sine theta 2. Well, whoops, let's, no reason to leave those vague. I can put a number in. Sorry about that. So these were 20 degrees. So now everything but M2 is a known quantity. And so if you plug in Chugsville all of that together, M2 is going to be, actually, we want to know the weight. It asks for the weight. You want to calculate the weight of the unknown sphere. So I'm just going to leave M2G alone and solve for the other stuff. And it's going to be 2 tangent 10, because sine over cosine is tangent, over tangent 20. And so basically 0.97, roughly 1 Newton is the answer in that case. So easy algebra, but you do have to slowly and methodically plod through the math there. All right. Let's see here. Quick poll here. Need a little break here. So I think you'll appreciate this. All right. Quick little poll. Just make sure people are still with us. Plus, I need a little bit of coffee. And so I brought my cold brew concentrate in suspicious looking bottles. And some hot water. And voila, instant bougie coffee. because I'm sort of a coffee snob. All right, 4 people not responding. We might have to send up EMTs. So, of course, all the people that picked number 1, guaranteed A's. No, just kidding. Watch everybody switch. We gotta have a little fun. Better to laugh than to cry. And math can do that. So, again, realize we know that this is mathematically challenging. It's totally relevant for the engineering group in the afternoon, and less relevant for life sciences. Not completely irrelevant, but not as intense. So know that there are people suffering more than you, if that gives you any comfort. But they asked for it. So, all right, let's end that poll. Thank you for the little lighthearted distraction there. Doing good, because we have just a couple more problems to do. The rest are test or extra credit. All right, so here's this situation. It's later this century when you can take a trip to the moon and not be a billionaire. And so there's going to be a spot between the Earth and the moon. There's going to be a spot somewhere closer to the moon because it's 100 times less massive. So somewhere off center, there will be a now if we call this total length between them r, okay, then that means if there's x kilometers between that magic spot, then there's going to be, actually I want to turn this around, at x kilometers from the Earth, before you get to the moon, then that means this little chunk is going to be r minus x. Okay? Now, when those gravitational forces are balanced, because we're closer to the smaller mass, we know it's off center, favoring the smaller mass, that's where the balance point will be between them. Well, since it's gravity, we also can't ignore that we're talking about we have to deal with the radius of each object. And so I could call this A and call this B. So here are a bunch of distances, some lengths that are critical to our gravity balance. And so last time we dealt with something like this was in Python, where we made all the orbits and whatnot. And so here we have this situation, and we've drawn a descent diagram. And here's the key idea, is we, at this spot where the mass of, say, this ship is for this transplanetary tour. Oh, and here again, I mentioned it earlier, that should be 10 to the 5th. This is 10 to the 3rd. All of these 10 with something else, so that's, oops, change it to red. That's 10 to the 24th, 10 to the 3rd, etc. So I forgot to re-superscript them, so be mindful of that. Same down here. That one at least has the minus in there. That gives you a clue. So here's what's happening. It must be the case at this spot. This is where the force of gravity of the Earth on that mass, okay, is going to equal the force of gravity of the moon on that mass. This takes us back to some of those interaction notations that we were dealing with earlier. Got to make that G a little bit better. It's a little better. And so, okay, force of gravity. Well, you've done the Newton's Law lab, or you're taking the notes on that. We've talked about the structure of that thing, and it's so big G, Newton's gravitational constant, different than little g. It's that 6.7 times 10 to the minus 11 times the product of the two masses. So we could have the mass of the moon and the mass of the earth, okay? And what are the distances for that? Well, it's going to be a plus x, and that gets squared. So recall that the general form of Newton's law of gravity is g, one mass times the other, over the distance squared, okay? And so the distance right there, that squared also didn't come out so good. So it's that distance squared part, okay? And so on the other side of this thing, it's the same structure. And actually, I need to, I'm being careful here. So I said that that was mass of the moon, and it's not. It's the mass that's right here. Got my coffee in me too late. So this mass and that mass. Okay, so this is the Earth mass of our ship or whatever interaction. So we were doing this in that Python lab. This is just a static version of essentially the same problem. And so now over here, we're going to have that same mass of the ship, but it's going to be the mass of the moon going here. But then I have more. I have an r minus x distance and a b distance. That is what's getting this is our distance squared business over here on that side. So this is a simple problem mathematically because it's just two well-defined forces that we've already covered in balance. It's that, and what's not obvious in the problem is, what in the problem is telling me balance point, and where you're awarding the certificate of passing from stronger influence of gravity, the Earth, to a weaker pull of the moon, or where's that spot where they're equal? Because on one side of it, Earth is more of an influence than the moon, and vice versa. All right. So, nice thing here is that, well, the gravitational constants drop out because it's the same everywhere. The mass is a factor of the ship in both cases, and now I just have what's the leftovers, and everything is known except x. So I have mass of the Earth relative to mass of the moon. Those are some really terrible M letters. And a plus x squared over all this other mess. All right. And of course, I got to unsquare root those things here. And so that gives us if we were to plug and chug all of the values into there. So you would get, let's see here, Earth 6 times 10 to the 24th kilograms over the moon 7.3 times 10 to the 22nd kilograms. That's going to equal 9.06, but that's also going to equal 6,400 plus x if we're looking at the values from above. You had 380,000 kilometers plus 1,700 kilometers. I just left it all in kilometers minus x. And so if you pull those together and flatten this out, multiply both sides by that denominator, you're going to get x is 343,144 kilometers away. So our final answer for this problem would be that. And it's just putting Newton's law of gravity in balance, because there is a balance point between the two bodies. It will be closer to the smaller mass body. The center of mass is offset in that direction. And there you go. Simple problem. All right. Number 14. Extra credit. Number 15. Extra credit. However, I will tell you this electric force, okay, what we end up getting here, and I'm making this extra credit because it involves a force we haven't dealt with, but the electric force, Coulomb's law, is going to be kq squared over, and this is when the charge is q for charge. Don't ask me why q is charge. It's because c is for the speed of light, so we had to come up with something for charge. All right. Will we get the extra credit per problem, or do we need to do them? Do them all? Basically, the extra credit is there so that if you give a reasonable effort, you will get extra points. And so basically, I'm going to use extra credit subjectively to fill in, give partial credit for things that are in need of extra credit points. So it'll be a per problem basis, and I'll just use them to help. The worst thing that could happen is you do nothing and you get no extra points. So it's basically that. So this is that electric force, and in this problem here, they're trying to figure out, is this thing stable? And if you could figure out the mass of the neutron, and so if someone makes a claim about the neutrons, here in, where is it? Since protons have the same charge, it's just positive versus, they're always far apart, opposite sides of the neutron. What mass of the neutron model if this model works? And so this person is proposing a model, and by the way, it doesn't work. Okay, so that's how you can know. And Newton's law of gravity has this structure. Notice they're both inverse square laws. So basically what's happening here is, in this problem, this electric force is in some way in balance with a gravitational force. I won't say that you should let them equal each other the way that they are. You're going to have to think about mass. This may be the proton, this will be the neutron. Do I have one or two or three, or what do I have? And then so you will let kq squared per d squared equal g product of some masses d squared, but there's got to be a factor in there that's not presently on screen. And so, given that everyone in this course, I've never had a person not already be multiple chemistry courses in. So you should have a good sense of, oh, it's going to be a factor of 2 or 4 or 3 or something, this proton neutron sort of thing. And so that's why this extra credit is you're using a new thing, and I'm forcing you to think about what other factor in addition to G would go on here given what we're dealing with, some number of protons, neutrons. So that's my hint on this extra credit. So this one here, largely, it's extra credit, and it lets you connect dots between this course and other courses. And that's always a good thing to do. We try to do that as much as we can in this higher education game. All right. This one, this is on the Coke, as is the next one. And that's the entire handout. So now you know there's a fair number that are extra credit. I think I have as many extra credit problems as I do test problems. And so I'll try to remember to make a separate handout of the extra credits. And I might just make individual one-pagers of each, and that way people can pick and choose. And then the rest are on the celebration. This celebration is something that will happen next week. And so I'll probably post it in the next couple of days for folks who are highly motivated.